to the cloud. So find the equation of a tangent plane and tangent line to the surface. Given function. All right, so we know, based off of experience, based off of the models that were given, that we haven't really explored yet. I was just thinking I might do something related to that as a form of a graded activity. Now, it's not hard. It's just something I'd like you to experience. All right. Find the equation of the tangent plane. All right, that's where we're starting. We know that we need partials. All right, so we have z is equal to, and remember, f of x comma y is thought of as z. And we're doing this for the a and b values of pi 0 and 0, 0 respectively. But let's take care of that in a minute. So for the sake of using nicer notation, we can take that z and make it an f. In multivariable functions, f and f of x comma y are thought of as the same thing. So you just replace it with an f and that's okay. F sub x, we'll chain rule going on here. So cosine of, and I'm going to write it as x squared plus y squared to the 1/2 power. Oh, sorry, negative sign. I'm so hung up on my notation there that I screwed up. Negative sign of blah, blah, blah. But then we want to take the derivative of this with respect to x. So it's going to be 1/2, still chain rule, work around the inner function, x squared plus y squared to the negative 1/2. Then we take the derivative of the inner function. In this case, with respect to x. So 2x, the y part of it goes to 0. So the good news about a function like this, structured like this, where x and y are not commingling, meaning they're not factors of the same product, there's not going to be a whole heck of a lot of difference between the partial with respect to x and the partial with respect to y. Because I'm still going to take the derivative of the outer function the same way. And I'm still going to actively take the derivative of the square root of x squared plus y squared. The only time that we're going to get a different result is when we actually take the derivative of the innermost function x squared plus y squared. In this case, the x squared is thought of as constant, goes to 0. Derivative of y squared goes to 2y. All right. So then we just have to evaluate the points. All right. So we have pi 0. And really, we kind of learned this in the last one. We need f of AB. We need the partial with respect to x of AB. And the partial with respect to y of AB. And then we do all that again for 0, 0. Right now, there's no expectation whatsoever that you do this by hand. So let me show you. And you don't need to get the three-dimensional surface in order to do it either. You could do it using Desmos. All right. There's definitely value in doing it by Desmos. So what we could do is we designate our function not in terms of x and y, but in terms of a and b. All right. So what I'm going to do is I'm going to just type an expression, but I can call it f. I can call it whatever I want. Call it y if you want. It could just be an ordinary computation too. I'll show you. If you do negative, so forget about letting it be equal to something, just negative sine of the square root of x squared plus y squared. Oh, sorry, I did the thing I said I wasn't going to do. A squared, because we want it to come up with a slider, plus b squared just making sure, times, and this is assuming you don't even want to simplify it, which I kind of don't want to do. So I'm just going to type it in just the way I have my expression here. So times, I got a 1/2 a squared plus b squared to the negative 1/2 times 2a. Right? And it creates the sliders, right? So I'll worry about that in a second, but before I go too far, I duplicate this and change it so that it's 2b. Right? And so then I can change my a slider to equal pi. Type in pi, pi. And my b slider, I want that. Well, actually, I could just use the slider there, assuming my my chubby fingers will let me do it. Oh, there we go. Surprisingly, it worked. Now you just got to keep track of what it is that you're trying to do. You know, so in the case, I didn't bother putting the original function in because I figured we could just do that pretty easily. You know, because you plug in a 0 for the y, it's cosine of the square root of pi squared, which is cosine of pi, which is -1. So that part is not, that's not difficult. But I now have my two computations, both of which give a result of 0. You know, that's pretty not bad. You know, just based off of the a and b values. But in terms of the computations, it wasn't that difficult anyway. But who's to say that we're going to have nice, clean numbers? You know, yeah, you throw in something, anything else, you know, like pi over 3. You know, you have pi over 3, comma 0. That's going to be clean for one function, but not so clean for the other. You know, just something to keep in mind. Anyway, as it turns out, in this case, the product at the end of 2x and 2y, you know, that's going to help things along pretty nicely, because when you have a y value of 0, when you have an x value of 0, the whole thing zeroes out. When you have a y value of 0, the whole thing zeroes out. So, you know, there's other ways. There's, you know, you can just do it computationally, but I wanted to take some time and show you how you would be able to use Desmos to support your work here. Okay. So in this case, I'm looking at undefined, undefined. Now, if I plug in a 0, this part equals 1, but we get undefined, undefined, which I would think kind of makes sense based off of the x squared plus y squared to the -1/2 power. All right, so 0 on the bottom of a fraction is going to be undefined. All right, so it's asking us to create the equation of a tangent line and tangent plane. Let me create some more room here. We can focus on the pi 0. So we know that z is going to be equal to -1 plus, well, you just follow the model. You know, it's the derivatives, which are both 0, times x minus a, y minus b, respectively. So in this case, it's going to be plus 0 plus 0. So z equals -1. It's a horizontal plane. Okay. So that's not too bad. For the other one, oh, we also need the the tangent line, but even still, that's not too bad because it's the A, B, and the Z values, right? So just with the slopes associated with them. So let me just get that there. So so the tangent plane. Oh, you know what? I just realized there's a little typo here, and I never realized this before. I've been doing this a long time. This should be a normal line. It's so weird. Because there would be infinitely many lines that are tangent at that location. Because any line that exists on that plane would work. I can't believe I missed that. That's what I call a legacy typo. All right, so the normal line x equals y equals z equals. All right, so the x value, what was it? Pi, right? So for this one, that's my A, that's my B. Yeah, so that's my A and my B, and then the slopes, which are easy enough. So pi plus 0t, so just pi. Then 0 plus 0t, so 0. And then the z part, right? The z part is the weird one. There's always going to be a t in there, right? So f of ab, which we know is equal to -1 minus t. All right. So that's the equation of the normal line. Now for this one, well, in 3 space, we can't really define anything as vertical unless we're saying it's parallel to the z-axis, and even still, that's a matter of subjectivity. So in this case, we can't really define a tangent plane at 0, 0, right? So in this case, neither would exist. So no solution for this part, right? Because, oftentimes we look at, okay, we got a slope of that's undefined. Oh, vertical line. But which way is vertical? And also vertical in 2 dimensions. Well, if I'm saying vertical is in the positive y direction, then I can't also say it's in the positive x direction. Right? So that's kind of a tricky proposition. Right. Well, anyway, so the notice at the bottom, what is the equation of a tangent plane at extrema? Not really so much of what is it definitively, it's what form would it be in if z equals some constant. All right, you write z equals c, where c is a constant, but I figured you'd probably be all right with this, shorthand way of writing it. All right. So what we're looking at is an extreme value. Right. We can see that there's definitely a hump in this graph, a high point and a low point. So they're talking about 3, 0, -1 specifically. Of 3, 0, -1. Geez, well, holy approximation. Pi 0, -1, right? Because the f of pi comma 0 ended up being -1. That gives you a coordinate here. Kind of hard to see, but if I bring it in very closely here, it's this point. It's just shooting down. I'm gonna get a thinner line there. Here's 3, 0. 3, 0, 0, I should say. And then we're shooting down, with a little bit of perspective going on. That gives you that point, 3, 0. And I keep saying 3. I don't know what's wrong with me. This is crazy. An approximation is one thing, but Christ. Really, pi 0, 0. It's just because I keep seeing that 3 on the number line, and I just kind of wanted it to be a 3. Pi 0, 0 is this location. And then shoot on down 1 unit, you got pi 0, negative 1. All right. Now, it's really hard to see, but this is kind of like a little bubble, right? You can see that little hump. You can see it's kind of like rippling down and then bubbling back up. If I kind of create a contour going around, you can see that we're creating sort of like a little ridge here, you know, or a little gully, if you will, or a ditch. And so what this is saying is that this point is a low point on this surface. Now, it's pretty safe to say that this point here would be a high point. It's just we didn't really address that because the point that we were given was 0, 0, if I'm not mistaken, 0 for x and 0 for y. And that corresponded to a 1. And actually, now that I think about it, it really should have worked. But there was something about the function that just kept it from giving us a slope. Right? Probably, discontinuity of some kind based off of the denominator. Yeah, the one location where the derivatives wouldn't exist. You know, it is what it is. You know, sometimes that happens. The idea is that if you know that you're dealing with an extreme value, then all you need is the z value at that location, and your tangent plane will be z equals that extreme value. So then it begs the question: how do we know something is an extreme value? That's a different conversation. We have a whole part of the unit dedicated to that. So stop this recording.